So let's get back to the math. So today we're talking about continuity. We'll be starting off with continuity and connectedness, and continuity, connectedness, monotonic functions, and discontinuities. Okay, so basically, okay. So in any case, we're going to start off with this theorem about continuity and connectedness, which gets us up to the intermediate value theorem. Okay, so this, remember I said that a lot of this class is clearing up things that were not really explained in your calculus classes. So one of them was the extreme value theorem, and you saw that that actually had to do with continuous functions on a compact set, right? The reason that the extreme value theorem worked, remember the extreme value theorem, which says that if you have a closed interval and you have a continuous function on that closed interval, right, so f continuous, then you're guaranteed a place where the maximum is attained, and you're guaranteed a place where the minimum is attained, right? There's going to be a place, right? There's going to be some place where the actual maximum value is attained, right? And there's going to be a place where an actual minimum value is attained. And that's used in Calc 1 or Calc 2, Calc 1 or Calc 2 to give you things like Rolle's theorem, which gives you the mean value theorem, which gives you L'Hopital's rule, and so it's really a crucial result, but they never explain it, right? Because they can't. Because in order to do so, you need to have compact sets, continuous functions on compact sets, right? So that was one result that was we were able to explain that we can now actually explain, and another result that we can actually now explain is the intermediate value theorem, right? So, does anybody remember how the intermediate value theorem works? You have some function, and it's continuous, right? And then you have two points of the function, and they have different values, right? Yeah, Eli.
It's if you for any value that's between f of a and f of b, there's some x between a and b such that f of x equals, we'll call it.
Yeah. So you're guaranteed. So if you have an f of a, if you have these, if your function is continuous and you have these 2 points have different values, you're guaranteed that there's some point between a and b where you attain that value, right? You're definitely going to hit that value. In other words, you skip no values, right? You skip no values, right? And so what that's saying is that the image is a continuum, right? In the language that we had before, this is saying that if you're looking at an interval and your function is continuous, then the image of that is still a continuum, which, as we saw before, is basically saying that the image is connected, right? Because we're in R1. Okay, so we'll say that like precisely in a few minutes. But what we need is the following theorem. So let's recall first the definition of connected. Right? So a function is connected. A set is connected means that it cannot be separated. Right? It can't be separated. Right? It can't be expressed as some union, A disjunct union B, where the intersection of A with B and the intersection of A closure with B and the intersection of A with B closure are both empty. Right? That's what connected means, right? It can't be expressed as a separation. Okay. Right. Okay. So we're going to go for the following theorem that says that, so as usual, we have some metric spaces. And you have function going from one metric space to the other. So the theorem says if f is continuous and the set E, a subset of x, is connected, then the image is connected. Okay. And as a corollary, we'll get the intermediate value thing. Okay. So let me just put up the corollary. The intermediate value theorem that says that if you have a function on a closed interval AB that's continuous, and let's say that f of A is less than f of B, then for every C in the interval of f of B, there exists an x between A and B where f of x attains that value. Okay, so that's what we were just saying over here, right? You have an A, you have a B, right? Let's suppose that f of A is less than f of B. You take some value between them, and you're guaranteed a point between A and B where that value is attained. Okay, and the proof is simply that the proof is just that by the theorem this is connected. So the image is connected, right? The image is also connected, right? And we saw earlier that in R1, right? Recall that in R1, being connected means that you've got this linear continuum property, right? That whenever you have two values in the set, you've got all intermediate values in that set. Okay. So connected basically gives you this linear continuum property. So that just immediately follows from this fact about the continuous image of a connected set. Okay, so I'm going to erase this because there's not much here, and I'll use this space for the proof. Okay, so let's get to the proof of this fact that the continuous image of a connected set is still going to be connected. And the way we're going to do it is by contraposition. So proof by contraposition. Right? We'll suppose that we'll show that if this is not connected, then E is also not connected. Okay, right? So we're doing, remember, contraposition means that instead of implying A implies B, you imply not B implies not A. Okay, so we'll show that if this guy is disconnected, then this guy must also be disconnected. Okay, so suppose that f of B has a separation right? In other words, f of b can be expressed as some union in A and B, where the closure of A does not intersect B, and the closure of B does not intersect A. Suppose f of b has a separation. Okay. And then we're going to use that to get a separation of E, right? Strategy, use that separation to get a separation of E. Right? We have a separation of the image. Let's pull it backwards and get a separation of the original set. Okay. Right. So here's our set E over here, and we're saying that that f of b, right? F of b is these guys together. F of b can be separated. Okay, so if it can be separated, we'll see that we'll pull this thing backwards and we'll use it to get a separation of E. Okay? Okay. So, right, so notice that E is contained in F inverse A union F inverse B. Right? F of B is A union B. So if we take the union of those pre-images, right, then we're going to cover all of B. Okay. So what we're going to do, we're going to use these guys. These guys will basically give us our separation. Okay. Right. We're going to say, okay, let's take E. It's contained in them, so we need to be a tiny bit careful. Let's let we intersect this guy with E, and we intersect this guy with E also. Okay, and then we have equality. Right? Now we have equality. Right? This thing was contained in that. Now we intersect that with E, and we have equality. And now we can use these guys to get the separation. Okay, so that's the main idea. And then the rest is just checking it. So let's see how that works. Let's see how all the pieces come together. Let's call this guy on the left G. Let's call this guy on the right H. Right. So we claim that this is a separation. Okay. And so E is disconnected. Okay. Any questions? Any questions? Okay. So right. So let me put up just an exercise. So a simple fact that whenever you take the inverse image of an intersection, it is the same thing as the intersection of the inverse images. That's pretty straightforward. That's a pretty straightforward exercise. Okay. So now observe. Right. We know that A intersect B hat. I'm sorry, B bar is empty. Right. So that tells us that. Actually, let me write it the other way. Doesn't matter. So I'm going to write A hat intersect B is empty. Right. So that tells me that an inverse of A hat intersect B is empty. Right. And I'm going to use this factor here. This tells me that F inverse of A hat intersect F inverse of B is empty. Okay, so I'm just using the fact that F inverse of an intersection is the intersection of the inverse images. Okay. Okay, and similarly, we have that F inverse A intersect F inverse B hat is also empty. Right? That's looking pretty good, right? Because you know what we want is to show that G hat intersect H is empty, and H hat intersect B bar G closure intersect H, and H closure intersect B, G are both empty, right? And you see what's going to happen here, right? Say well. F inverse A bar certainly includes F inverse A, right? Okay. F inverse A includes G, right? Because G is the intersection of that with E, right? Okay, but notice by continuity. F inverse A bar is closed. This is the place where we use the continuity. This is the only place, and this is the important place where we use the continuity. Okay. This is closed because we're taking the inverse image of a closed set. Right? Continuity means that when you take an inverse image of an open set, you get an open set. Inverse image of a closed set, you get a closed set. Right? This is closed. So when we get, if we close G, it's still going to be inside there. Right? G was sitting inside this closed set. Well, then G closure is going to sit inside that closed set as well. Right? Because closing, this set was already closed. Right? So throwing in the limit points of G, well, they're already included in the closure here. Right? We don't have any trouble. Okay. Okay. So so now this guy sits inside of F inverse A bar, right? And H, remember what H was? H was this guy. This guy sits inside of F inverse B. Right? Those were, this and this were disjoint, so we know that G bar intersects H is also disjoint. Okay, and we do exactly the same argument in the other order to show that. So similarly we get that G intersects H bar is empty, and so we've got a separation of E. Okay, any questions? Maybe talk to somebody for half a minute. See if you can come up with a question. Turn to your neighbor and explain to them how the proof goes.
Connected. So it's by Right, you have like these two subsections that from and like you're using it from a speed of one with the closure of the other, and vice versa.
Okay, let's get back to it. Okay, so let me just say one thing. So the idea is simply that if the image has a separation, you pull those sets backwards, and that basically gives you a separation of the original. Okay, the separation of the image you pull backwards through the continuous function, and that basically gives you a separation of the original. Okay, it's not exactly right because this is contained in here. It's not actually equal to the set. So you have to be a little bit careful. But that's basically the idea. So actually in my notes I have it wrong. I have it written that E equals this thing. E equals this thing, and I mess up. I have I don't have G and H. I just show that this thing is a separation. Okay. Right. So that's actually wrong. But it's kind of clearer to see if you pretend that this actually equals it. Let's just for a moment let's pretend that it equals. Okay. We'll see how this would give you a separation. Okay. So what we have to do is we want it for this to be a separation. We want to see that F inverse A bar intersects F inverse B is empty and vice versa. Right? That's what we would want. Right? We would also want the other statement. Right? This thing is empty. Right? That's what we want for this thing to be a separation. Well, look, we already know that F inverse A bar intersects F inverse B is empty from over here. Right? Right? We know that because A and B were a separation over there.
And then
Okay, and then okay, so we actually know this, and then we say, well, does this give it to us? Does this give us that this thing intersect that is empty? And you realize that, well, look, if you use the key fact, right, that this thing is closed, and it contains F inverse of A, right? Since it's closed and it contains this thing, it will contain the closure of that as well, right? And so that shows you that this statement implies that statement. Okay, so I don't know if that makes that should make it a little simpler. Yes, Gene.
So do we automatically have the intersection of the inverses of A closure and B is non-zero even if F and B has a separation?
So,
like, is that a given? On the front like that top line, is that a given because we start with F and B has a separation, or is that?
that follows from here. That follows from here over here because you know that A and B are a separation, right? So that tells you that this thing is an empty set. Well, then F inverse of that empty set is an empty set, right? But then by the exercise, that tells you that the intersection of these inverse guys is also empty. Okay. So yeah, so this thing over here is just a consequence of this being true for any function, in fact, not even continuous. Where we use the continuity is to get from here to here. Okay. Right, we say, well, look, this guy actually is contained in this guy. So of course its intersection with this is empty, right? Right? The bigger set intersect this thing is empty, right? Certainly the set that's contained in that bigger set intersect that guy is empty. Okay. 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 That's not like I said, there's a mistake in that argument, but that's basically the real argument, right? I mean, that's basically, the rest of the argument is just sort of making sure that you actually have E rather than some set that contains E. So, okay. Okay. So, discontinuities. Discontinuities on R1. Okay. So, first thing we're going to do are so-called right limits and left limits, which are things that you might have seen in Calculus 1, right? It's basically this idea of you have some point, right? You have some point, and you're approaching that point from the left-hand side only, right? So, right, you have some function that looks maybe like this, right? It doesn't have a limit at that point, but it has a left-handed limit and it also has a right-handed limit, right? So this is the picture. Okay. So here's the definition using the epsilon delta language. So again, the setting is that you have some function on an open interval. Okay, and you have some point. You have some point in the half open set, half open interval. Okay, so here's the definition. If there exists a Q in R with the property that for all epsilon greater than 0, there exists a delta greater than 0, such that if P lies in x plus delta, then f of P lies in the epsilon neighborhood of Q. Then we say the right-handed limit is Q. So the right limit at x is Q. Okay, so again, the picture. This is all notation, and it seems kind of maybe it seems kind of opaque. But just keep in mind the picture, right? So the picture is this. There's this Q. Okay, this is Q, and it has the property that given any epsilon neighborhood. So here's x sitting inside of AB. Okay. This guy has the property that given any epsilon neighborhood of Q, right, there's a delta neighborhood, there's a right-sided delta neighborhood. Okay, so there's this guy here, x plus delta. Okay. Given any full epsilon neighborhood of Q, there's this right-sided neighborhood of x. So that everybody in the right-sided neighborhood of x lies in the epsilon neighborhood of Q. Okay. Right. And if you can do that for every epsilon, then we say that the limit from the right-hand side is Q. Okay, turn to a neighbor and say, the only difference between this and the limit is blah. What's the difference between the right limit and the full limit?
Like if you make it small enough and you have some small
It's in the left.
probably because that's so much. Because it's all over diagonal spaces that are, if you take it one left or side, then it's just how much is it? So yeah, I guess
Okay, can somebody tell me? Can somebody tell me what the difference is? What's the difference? What would I need to change here to make this a full difference? What would I need to change here to make this the actual definition of the limit Fairbox?
it would need to be element of x minus delta, x plus delta.
Right. So the only difference is that instead of taking this half neighborhood, I would take the full, actually the full punctured neighborhood. So I'd have to be like x minus delta, x plus delta star. Right. That's the only difference, right? Everybody okay with that? Right? That's the only difference between this, the right limit and the full limit. Yeah.
I'm wondering how you would define left and right limits on like non-one-dimensional space.
You can't.
Oh, so they're okay.
Yeah. So that's why this is in R.
Okay, great.
That's why this discontinuity is in R. Okay, so that's the right limit, and similarly, one defines the left limit, right, so x negative, right, and you notice that if the limit from the left and the limit from the right are the same, then that would mean that given any epsilon, you can find an interval on the right and maybe an interval of different length, different radius on the left, where everybody inside here gets into the epsilon neighborhood. Right? So here's my x, here's my q plus epsilon, q minus epsilon. You'd be able to, if the right limit exists, that means you can find a delta that works over here. If the left limit works, then you know that there's a delta on the left that works. You take the smaller of them and you've got your punctured neighborhood. Right? You take the smaller of them, then you've got that's the radius of your punctured neighborhood, and that would give you the full limit. So if the limit from right and the limit from left exist, then you know that the limit actually exists. Right? The existence of both of those right and left limits implies the existence of the limit, and vice versa. Okay. So here's the definition. We're going to be talking about discontinuities of functions. If the left limit and the right limit exist, but f is discontinuous at x, we call x a simple discontinuity. A simple discontinuity, or a type 1 discontinuity. And then type 2 continuities are anything else. Okay. So, type 1, so simple discontinuity means that the left limit exists and the right limit exists, and they're just not equal to each other. Right? Other kinds of discontinuities, you can have something like sine 1 over x as x approaches 0. Right? Neither the right nor the left limits exist in that case. Right? And it's discontinuous at 0. Yes?
Could you just repeat again what chapter is, but f is something at x sort of from the definition, I just can't quite see it. Discontinuous? On the far right.
Over here? Oh, if the limit from the left and right exist, but f is discontinuous at x. F is discontinuous at x. So I always abbreviate continuous as CTS. Okay. So our main goal at this point is to get to a theorem about monotonic functions, the discontinuities of monotonic functions. This is kind of a nice application of things that we've seen before, of like supremum system. So our goal is to see that the set of discontinuities of a monotonic function is countable. Okay, that's where we're heading towards. So let's put out some definitions. Okay, so first off, so again we have a function on some open interval. If x being less than y ensures that f of x must be less than or equal to f of y, that we call f monotonically increasing. Okay, so this is just what you would expect, right? Right. We want to describe a function that increases, right? What is it? How do we describe that other than how do we describe that mathematically? We say if you take 2 points, then the value on the left is less than the value on the right, right? So it's just the way you think it ought to be. Right? The value of the left-handed point ought to be less than or equal to the value of the right one. So that's how we formally define monotonically increasing, and similarly for decreasing. Right, we would just flip the inequality here. Okay, so now comes our theorem, our first theorem. Before we get to the goal, is the following. If f is monotonically increasing, then 2 things happen. One, for all x in the interval, the left hand and the right-handed limits exist. Okay. And second, if you have two values, one less than the other, then the right-handed limit of the left guy is less than or equal to the left-handed limit of the right guy. Okay. This is sort of, I think the second one is kind of obvious. Is that's kind of intuitive, right? The right-handed limit, if you've got a function that's increasing, and you have 2 points here, then the right-handed limit of this guy is going to be less than the left-handed limit of that guy. Right? That's kind of you would expect that. Right? This one is maybe not as obvious, that if your function is monotonic, you're guaranteed left and right-handed limits. Okay. But I mean, I don't know. For this, we're going to need to use the idea of supreme. Notice that this tells you that monotonic functions only have simple discontinuities. Right? They can't have type 2 discontinuities. Okay. So okay, so let's pick some x and a b. Okay, and we want to see that the limit exists, right? We want to show that there's some left-handed limit. We want to show that the left-handed limit exists, and you can kind of guess what we're going to do, right? Let A be the supremum of all the values of t, of f of t, where t is smaller than x. Right, so here's your picture. A, B, here's x, right? You take all the values, let t be anything smaller than x, right? And then you look at all the f of t's, right? Look at all the f of t's and take the supremum of that. We're going to claim we claim that the left limit is at A. Okay, so here's the picture. Here's the A. We're claiming that that the supremum of all these guys is the left limit of x. Okay. Okay. So this is sort of just like this is basically just chasing definitions, right? We want to show this thing as the left limit. What do we have to do? Recall, we need to show that given any epsilon, right, there exists a delta such that there's a left-handed limit, there's a left-handed interval here in which all values are within epsilon. Right? So we say, okay, somebody gives us an epsilon. Can we find a delta that works for it? Right? We have to be able. That's what we need to do to show that this is the left limit. Right? And so we say, okay, right? Given a epsilon, we need to show given a epsilon, blah 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 blah. Okay, so given an epsilon. Let's say, yeah, we know there must be some point T naught in A comma x where f of T naught is bigger than A minus epsilon. Let me draw the picture again over here. Here's x, here's a b, here's my function, here's a. Somebody has given me an epsilon, right? We know there's got to be somebody on the left side over here. There's got to be some point T naught where we're higher than a minus epsilon. Right? If there's nobody there, then what? If there's nobody if there's nobody over here where the values are bigger than a minus epsilon, then why is that wrong? Yes?
There's no limit. There's no left side limit.
Well, that's not the problem. What was A? A was the supreme, right? If there's nobody over here bigger than A minus epsilon, then A minus epsilon would have been your supreme. Right? A minus epsilon would have been your supreme. So there's got to be somebody there bigger than A minus epsilon. Right? And otherwise, A is not the supreme. Right? So we know that there's some place where you exceed A minus epsilon, but the function is increasing, so you know that since f is increasing, you know that in t naught comma x, f of t is bigger than A minus epsilon. Right? Everybody in there is going to be bigger than A minus epsilon. Right? Because at this point you exceeded it, and you never get any smaller afterwards. Okay. So we found our left-handed interval, right? We found the interval. Here it is. It goes from t naught to x. Right? So just like your delta, the x minus t naught will do. Okay. So, right? So given an epsilon, we found the delta that works. Right? So that tells us that this thing is actually A. Okay? And we could do the same thing from the other side to show that right-handed limit works. We would take the infimum of values from x to b. Okay. Any questions about that? You guys getting it? Yes? No? Kind of? What's the idea? Always think like, why does this make, you always want to think like, why is this completely obvious? Okay? That's how you want to approach it. Like think, why is this completely obvious? Okay? You think, okay, I'm trying to find a left limit of this guy. What am I going to do? I'm going to take all the values on the left and take the least upper bound of them. And my function is increasing. Right? So the greatest value ought to be the left limit. Right? The greatest value I can get. So I look at all my values to the left of my point, and I take the supremum of that. That ought to be my limit. Right? And then you use the property of the supremum to see that it actually is the left limit. Okay. When I got to the end of my college experience, a friend of mine walked up to me and said, I wish that they had told us that everything was actually easy. Because when we were doing it, it felt so incredibly hard, right? When you're doing it, it's like, my God, this seems so incomprehensible. But in a year or so, you'll look back and you'll be like, what? This is actually not that. This is actually not that hard. Okay. So don't be intimidated. Okay. You will. This is a little bit akin to my realization of eternal youth. So, so some years ago, I realized that 5 years in the future, I'm going to look back and see myself and say, boy, was I young. Right? In other words, the way you are right now is always young. Okay, yeah, so this is the corollary, it's a corollary of the theorem that all mathematics is easy. Okay, Yeah, that's not true.
Hindsight is 20/20 theorem.
Basically. Okay. Let's get on with it. Let's get on with it. Okay. So the other thing we wanted to show is that when you have 2 points, one to the left of the other, then the right limit of the left guy is less than the left limit of the right guy. Okay. So again, this is sort of an obvious thing, right? So you've got these 2 points, x and y. You've got your monotonically increasing function, right? And then you look at the right limit, right? You look at the right limit of this guy, and you look at the left limit of that guy, right? And the right limit of the left guy will be less than the left limit of the right guy. Right? So that's sort of intuitively obvious. Let's just write down how that works out. So recall, so we want to show that fx plus is less than or equal to fy minus. Right? That's what we want. Right? We want that to be true. Okay. Now remember how we got fx plus from the previous step. Fx plus, remember, was the infimum, right, of the values on the interval past x, right? Fx plus was the infimum over this set here, right? And fy minus was the supremum of the values on the left, right, to the left of y, right, the values over here, right? But the infimum of these guys equals the infimum over this interval here, right? Because the value, these guys over here are greater than these guys over here. So throwing them out doesn't change the lower bound, right? So I can throw out, I can restrict this to just the values between x and y without changing the infimum, because these values are bigger. Values over here are bigger. Similarly, I can throw out the guys to the left here. Okay, and so you see that this is obvious, right? That the infimum, right? Certainly the infimum over that set is less than or equal to the supremum over that set, right? That's what you wanted. You wanted to show the up guy is less than the bottom guy. Any questions? This is not particularly exciting. So if some of you are feeling sleepy, that's you should be feeling sleepy. Yeah. But it's still worthwhile to show you something. You know, just as a matter of craft, right? And you have to see how everything works, not just the fun parts. Okay, so the last result is this theorem about monotonic functions. So suppose that f is monotonic on AB, then the set of discontinuities is countable. Okay. So here's the idea is pretty. This is pretty straightforward. You say, okay, well, we know from what we saw earlier, right? Recall that all discontinuities monotonic functions are simple. Right? All of them are simple, so we always have, there's going to be some left value, and there's going to be some right. There's going to be a left limit, and there's going to be some right limit. Okay. Right. And we have that, we know that one is going to be, the one from the left is going to be strictly less than the one from the right. So if x is a discontinuity, then we know that the left limit is going to be less than the right limit. It can't be equal because then it wouldn't be a discontinuity. Okay. Okay. So now choose a rational number R of x that lies between those two values. So we're going to associate each discontinuity with a rational number. That'll mean that that the set is that the discontinuities are countable. So that's basically the end. The only thing is that you have to, so if y is another discontinuity, let's say that y is to the right of x, by part 2, by what we just showed in part 2, we know that f of y minus is bigger than or equal to f of x plus. Right? So Ry will be strictly bigger than Rx. Right? So the only concern is maybe that you associate the same rational number with two discontinuities. Right? But that can't happen because right, if you have your x and you have your y, and you have these two discontinuities, right? Your first number is going to lie between these two values, right? So it's less than f of x plus, right? But f of y minus is bigger than f of x plus. So you're guaranteed that your R of y is strictly bigger than your R of x. Right? So that gives you that you have a one-to-one map from. I'm sorry. You have a one-to-one map from the discontinuities to the rational numbers. Okay. So that shows you that the discontinuities are countable. Or finite or maybe countable. Okay, so there's a little bit left in this chapter. It's about limits at infinity. Let me just use the last couple minutes to say a little bit about that. There's a little bit about talking about things like as x approaches infinity, f of x equals some value L, say, right? So the only difference here is that, so the definition of this thing will be like this. It'll say, given any epsilon, there exists an n, so there exists some number n, such that if x exceeds n, then f of x, the distance of f of x from L is less than epsilon. Okay, so right, remember when we're talking about approaching some finite point, the difference is we say there exists a delta such that if x lies in the delta neighborhood, the punctured delta neighborhood of x naught, etc., etc. Right? So, talking about the limit, we say given an epsilon neighborhood, there's a delta neighborhood of x naught in which we're that close. Over here, we're saying given an epsilon neighborhood of L, there's this neighborhood of infinity. You want to think of this thing as like your, where this guy here is the punctured delta neighborhood of x naught. This thing here is basically your punctured end neighborhood of infinity. Right, so the picture you want to keep in your mind, it's basically the same idea. Right? So here's my x naught. Infinity, of course, doesn't exist, it's way over there. Right? And here's L. So, for the limit to be L means given any epsilon, there's a punctured neighborhood of x naught, there's a punctured delta neighborhood of x naught in which your values lie inside here. Right? For infinity, it's like this. There's an n past which all your values lie inside here. Right? Past which all of your values lie inside here. So this is really, you want to think of this as your neighborhood of infinity. Entirely analogous to the neighborhood of x naught. Okay. Right. Those of you who go on to learn complex analysis will be excited to know that, that in complex analysis, one identifies sometimes the complex plane with a sphere called the Riemann sphere. So every point on the plane is identified with a point on the sphere by stereographic projection. That is, you take the North Pole and you run a ray to the point in the complex plane. And you say, okay, where does my ray intersect the sphere? And I'm going to identify those 2 points. So this Z here, I'm going to identify with this Z here. Right? So the whole complex plane gets mapped onto the sphere. But then there's this point that's missing at the top. Right? There's a hole at the top. That's infinity. Okay. That's actually infinity. It's the North Pole. Okay, that's it for today. See you guys later.
Thank you.